about the physics of earthquake modeling. And for the first class and the second class, I explained the friction law that plays an essential role in understanding earthquakes. And this is what we saw yesterday. And mu is the friction coefficient. And this friction coefficient is a function of slip velocity v and the state variable theta. One can figure out that friction coefficient is a function of slip velocity. But the nature of friction is rather more complex, so that it depends on an additional variable theta, which is a function of time itself. And this time evolution effect of theta is responsible for the slow relaxation process of the friction force. And the formulation is as follows. So in this formulation, one cannot say anything about the absolute value, but can say about only the changes from an arbitrary reference state. Here, the reference state is taken such that a friction coefficient at slip velocity v and the state v star and state variable theta star. And this v star is a reference slip velocity which can be chosen arbitrarily. And usually this theta star is chosen as the steady state value of the state variable at this slip velocity. So, so this states that friction coefficient, the change of the friction coefficient from this reference state is a function of slip velocity and the state variable, and these dependents are both logarithmic. And here we have a non-dimensional constant a and b, which are purely empirical. And in most experiments, these constants are on the order of 10 to the minus second. So these are very small dependence on these quantities.
The state variables, how do they change with the surface finishes?
Surface, sorry?
We have the roughness.
Yes.
We have asperities and certain, probably some statistical parameters can be used to describe that surface.
Yes.
It obviously depend on that.
It's yeah.
Is there any correlation being made with that?
That's a very important question. Actually, usually this state variable, especially the time evolution of the state variable, should depend on the details of such surface topography. And but to describe this empirically, we need to seek for a simplified time evolution law, like this kind of empirical law. And here, the length constant L comes into play. And this is actually interpreted as the typical length scale for the surface roughness. So in that respect, the surface roughness comes into play for the time evolution of the state variable. But this kind of time evolution equation is always determined empirically. And actually these two are popular, but these two cannot do a perfect job in describing the relaxation behavior. For some cases, this overestimates the friction coefficient. And also this law cannot describe the aging behavior. Actually, this term denotes the aging behavior of the frictional surface. Roughly speaking, if theta increases, the friction coefficient also increases with respect to the logarithm of the state variable. So if the slip velocity is 0, which means that the surface is at rest, but even if the surface is at rest, then this state variable increases with time. And this means that theta equals t. So this means that this friction coefficient increases with the logarithm of time. So this is why I call it aging law, as it describes such logarithmic aging of the friction coefficient. But in here we don't have such terms. But it can describe the dynamic relaxation behavior better than aging law. So each of which has its own good point and own bad points. So there is no perfect time evolution law for this state variable. So this is a kind of open question to seek for a better evolution law for the state variable. So this is more 20 years ago, but if you are interested in this empirical friction law, this review paper is still good in understanding the details of such formulation. And also, as I explained yesterday, this empirical law can be interpreted from an atomistic point of view. And that kind of derivation is given by, in my own work. And also, this logarithmic dependence itself can be derived using dimensional analysis. So this is also given in my own paper. So this is the starting point to understand the frictional instability that is related to earthquakes. So in this class, I'm gonna mention the following. How can we understand earthquakes based on this empirical law? But the important point is that this empirical law is valid only for quasi-static slip. Say the slip velocity is smaller than 1 millimeter per second. So if the slip velocity is larger than 1 millimeter per second, there is no phenomenology known for such high-speed friction. And that hinders our understanding for earthquakes. But at least we know empirical law for slow slips. So I explained yesterday that or Monday that the real particle velocity on the earthquake faults, which means that the slip velocity on the earthquake fault is about 1 meter per second at maximum. So, and this is the steady motion of the tectonic plate. So, during earthquakes, the slip speed of earthquake fault is at somewhere, and it is accelerated from below to some point, and then decelerates. So at least using this quasi-static slip, one can describe this acceleration behavior that leads to earthquakes. So we're gonna see how this is accelerated. And actually, we can derive some quantitative condition for which slip becomes unstable. So on Monday, I explained that the earthquakes can be regarded as the frictional instability. So this is a cartoon for subduction zone. So usually, oceanic plate wants to go beneath the continental plate. But because there is friction between two tectonic plates, due to the motion of the oceanic plate, this continental plate undergoes elastic deformation. And at some point, this elastic restoring force exceeds the friction force. And then this interface undergoes abrupt motion, which leads to earthquakes. So this is a very simple image or scenario for earthquakes. But this such a simple story is not generally true because the friction is much more complex than this kind of threshold behavior. For example, this is also a more realistic cartoon for subduction zones. And sorry about Japanese. And, but this is a oceanic plate. And there are several regions that can be classified according to their seismic activities. So gigantic earthquakes occurs only around here, these blue thick lines, which means that large earthquakes cannot occur at the very deep part or at the shallow part. So it occurs only in the intermediate depth of this subduction zone. And surrounding this seismogenic zone, there have been known that kind of slow earthquakes happen here. But here I don't have time to explain what slow earthquakes are. So we just say that earthquakes does not occur everywhere in the subduction zone. So it may have some special condition for earthquake type instability. Sorry, we skip this. So on Monday, we have seen this for the continuous spectrum for the frictional instability. So this is a rather steady motion, while this is unstable motion. And the only difference is just a difference in normal load. So this is smallest normal load, and this is the largest normal load. This means that if the normal stress is small, then there would be no earthquakes. So apparently, the normal load plays an essential role in the frictional instability. So we can understand this quantitatively using this friction law. To understand this, we should begin with this kind of 1 degree of freedom system, which we have just seen in the movie. So this is an elastic spring with spring constant K with connected to mass. The mass is m, and there is a normal load pushing the object from top. And between this object and substrate, there exists a frictional force, which is proportional to this normal load. And this friction coefficient is described by this empirical law. And this endpoint of the elastic spring is displaced at constant velocity. So the equation of motion can be easily written like this. So this is the acceleration term of the position of this object. And this is the elastic force. And elongation of this spring is just rewritten by this because the endpoint is displaced at constant velocity. And this term describes the friction coefficient. So this depends on the normal load and slip velocity and the state variable. And intuitively, one can obviously see that for infinite spring constant, this object undergoes steady motion with the same velocity imposed by a hand or something. So this is a steady motion. So we're going to see how this steady motion destabilized. To do this, we just do a standard linear stability analysis by considering the small perturbation to this steady state motion. So, and then the equation of motion is written with respect to this perturbation term. And here, this is a nonlinear friction. So we must linearize this friction force with respect to the perturbation. And by considering this perturbation, the slip velocity is also perturbed by x dot. And because this is a non-steady contribution to the velocity, the state variable are also perturbed by this term. So we're going to write this perturbation to the state variable as s, as a function of time. And because this steady state is L over V, so we can write the state variable like this. So using this, we can linearize this deviation of the friction force from steady state. So we end up with these two differential equations. And because this is second order time derivative, we should include an additional variable, which may be just x dot. So what we obtain is three differential equations for which are first order derivative in time. So it can be a good exercise to show that these differential equation system undergo supercritical Hopf bifurcation at some critical spring constant. And this critical spring constant is described like this by using the B and A, which are contained in the friction law, and L is also contained in the friction law. So actually, this 1 degree of freedom system undergoes Hopf bifurcation at some points. To calculate this, it is much easier to consider the massless case. So, and in this case, this is just, we can consider 2 by 2 matrix to obtain eigenvalue. But in any case, the important parameter in the instability of steady motion is the spring constant. For infinitely stiff or sufficiently stiff spring constant, the motion of the block is steady. But beyond or below this bifurcation point, we have Hopf bifurcation and mass motion of the mass is oscillation type. And this kind of behavior is beautifully seen in experiment. And this is one of the most famous papers in that literature. And actually, this is a sheet of paper pushed on the substrate. And they measure the force acting on the paper by this spring. So if this stiffness of the spring is sufficiently small, then we can see this kind of bifurcation from steady state to oscillation phase. This is the time, and this is a displacement or horizontal displacement of this spring. And in experiment, it is rather difficult to change the elastic constant. So in here, they just change the normal load. So for the small normal load, the motion is stable. But if we increase the normal load, then the system becomes more and more unstable. And this is another example. And this is not a paper case. And actually, they have granular matter as the substrate. And here we have some object made from something, I forgot. And yeah, they measure the stick slip motion in the same manner, like this. So this is a steady motion, and this is oscillatory motion after the Hopf bifurcation. And in here, they don't change the normal load, but rather change slip velocity, this constant driving velocity, and see the bifurcation. But actually, this is contradictory to this condition, honestly. Here, of course, this critical point depends on the driving velocity, but it would be an increasing function. It means that if we increase the driving velocity, the system becomes more unstable because the critical stiffness becomes large. And below this Kc, the system is unstable. So according to this prediction, for larger driving velocity, the system is more stable. But what they observed here is just opposite. So actually, from bottom to the top, they decrease the driving velocity, and the system becomes more unstable. So this experiment is contradictory to the theoretical prediction that we still don't know, don't understand. Anyway, but at least for this kind of simple system, we can predict the behavior of the system like this. So this stiffness plays an essential role. And if this stiffness is sufficiently small, it means that smaller than this value, then the steady state motion becomes unstable. So this means that the stiffer system is more stable, and the softer system is more unstable. And because the spring constant must be positive, so that this B minus A must be also positive to obtain the stick-slip behavior. So recalling that the steady-state friction coefficient is only a function of slip velocity, and this is a function of logarithm of the slip velocity. And the proportional coefficient is A minus B. So B is larger than A means that this slope is negative. It means that friction gets weaker for faster slip. So intuitively, this kind of negative dependence would lead to some kind of instability. And actually, this is quantitatively expressed by this condition. So for this system, to be unstable, we need to have negative velocity dependence of the friction. And the spring constant must be smaller than this critical value. So this is the case of 1 degree of freedom system. And then we move on to the continuum case. But actually, for continuum case, we can directly use the knowledge obtained in 1 degree of freedom system. So in that respect, 1 degree of freedom system is very instructive. So let's consider this case. So suppose that we have two elastic plates, and the thickness of these two plates are both denoted by h. So they have the same thickness. And Xi1 is along this direction, and top part of the top plate is displaced at constant slip velocity v0. V0 to this Xi1 direction. And we can easily show that spatially uniform state of this continuum becomes unstable for negative dependence of the friction on slip velocity. So in this case, the velocity dependence is also plays an essential role in the stability of slip. To do this, we can also resort to linear stability analysis. So we consider the relative displacement from the top plate to the bottom plate as a function of Xi1 and time. So the displacement would be something like this. So this is the motion at constant velocity, and this is displacement of the top plate from the top to this interface, which may balance to the deformation inside the top plate. So this part is the steady state part, and this part is the perturbation part. Here we consider sinusoidal perturbation, and the amplitude depends on time. So we consider how this amplitude dies away or increases. And here kappa is the wave number of this perturbation. So one can compute the shear stress produced by this displacement. And this part leads to steady state shear stress caused by the elastic deformation. And this term is responsible, this term is the response to the perturbation, which is proportional to the displacement, amplitude of displacement, and the proportional coefficient is interpreted as the spring constant to this perturbation. And this spring constant depends on the wave number of the perturbation. And this spring constant can be explicitly computed from a theory of elasticity, like this. And G is the shear modulus of these materials. And kappa is the wave number, and H is the thickness of this hyperbolic tangent. So we know the shear stress acting on the interface so that it should balance to the friction force. So it gives you linearized differential equation with respect to the amplitude of the perturbation. And this is, again, the perturbation to the state variables. So actually, this is exactly the same as we had for 1 degree of freedom system. But in this case, we don't have mass term. So the problem is more simplified, and it is straightforward to show that this differential equation undergoes Hopf bifurcation at this critical stiffness described by this. Sorry, here sigma n is the normal stress to the interface. And L is the characteristic length scale for the state variable evolution. And so this result is essentially the same as in the case of 1 degree of freedom system, except for the wave number dependence. So we're going to write explicitly the wave number dependence like this. So because this hyperbolic tangent is, increasing wave number, is it a decreasing function? Okay, so this is the increasing function with respect to the wave number. So large wave number leads to a larger spring constant, which means that the perturbation is more likely to be stable. So we're gonna see more explicitly. So this line is wave number dependence of the spring constant. So for shorter wavelengths, the spring constant is larger. And Hopf bifurcation described by the how large or how small this line is compared to this critical value. So if the spring constant is larger than this critical value, then the system is stable. And the spring constant is smaller than this value, then system is unstable. And this intercept is G over 2H by taking the limit of kappa goes to 0. So if this intercept is larger than this value, then we don't have an unstable region like this. And this kind of situation is realized for sufficiently thin plate, because H must be small for this interception to be large. And this is intuitively understandable from daily experience that if one rubs some object to a substrate, thin object is more stable, but thick object can cause stick slip motion. So in both cases, the stability condition is written like this. So it also involves the thickness. For the case of earthquakes, we should think about sufficiently large thickness as we are considering the tectonic plate. And in this case, the spring constant looks like this. So the condition for Hopf bifurcation is written like this. And this defines the critical wave number below which the perturbation becomes unstable. And in terms of the wavelengths, the critical wavelength is proportional to the length scale in friction law, and inversely proportional to the normal stress. And this is a shear modulus. And so if the perturbation and the wavelength of the perturbation is sufficiently larger than this, then the perturbation becomes unstable. So actually, how large is this critical wavelength? For example, if the normal stress is 1% of the shear modulus, which may be sufficiently large normal stress. And this is a typical value obtained in experiment for empirical parameters in friction law. Then this lambda c is proportional to the length scale in friction law times 10 to the fifth. So this wavelength is particularly important in considering earthquakes or any other unstable motion. So it is determined from this length scale L, which might be related to the topography of the surface. So as I mentioned, this length scale in friction law is on the order of microns. Then this critical wavelength is about 10 centimeter. Okay. So okay, so this lambda c denotes the wavelength, and if the perturbation is sufficient, perturbation has larger wavelengths than this, and that perturbation is unstable. And this is easily extended to patch-like perturbation. At the last part, we have seen the sinusoidal perturbation, plane wave perturbation, but here we consider patch-like perturbation, which spans 2r on this interface. And in this patch, the displacement is perturbed to some extent. And if such if we put some perturbation to a patch embedded in a continuum, then the shear stress drop and the maximum displacement, the displacement on the interface is described by this relation. And this relation can be calculated by the elasticity theory, which may be very complicated. So we just use the result like this. And this is just a numerical factor. And this x and y is just coordinate on this frictional plane. And we consider circular patch of radius r. So the position in this patch is described by x and y. And this means that at the center of the patch, the displacement is the largest. So we focus on the central part of the patch only and consider the relation between the displacement at the center and the shear stress to drop at that position.
Can you begin winding? Can you finish in a few minutes?
Yes. Finish?
Yeah.
Yeah, yes, I have 10 more minutes, right? Yes?
Why not?
So this says that shear stress is proportional to the displacement. So this plays a role similar to the spring constant. And this spring constant is proportional to the shear modulus, which is intuitive, but inversely proportional to the size of the patch. This means that for larger patch, we have a softer system for the perturbation, which means that if the patch gets larger, then such perturbation would be more unstable. So we can exactly use exactly the same discussion as we have seen before using this spring constant. And this leads to the critical radius of the patch at which it becomes unstable. And this is described by the same expression as we saw before. And this, by using this gives a critical patch radius at which the perturbation becomes unstable. So if the perturbation exceeds this critical value, that patch undergoes unstable motion. And such tendency is clearly seen in experiment. And this is again taken from an experiment using the transparent material. And here is the position along the slip direction. And this is time. So it's a spatial-temporal diagram of the slip. And this dark region corresponds to the slipped region. And the bright region is a sticked place. So this means that slip occurs around here, then it slowly extend its size. But the motion is still not very fast, but at some point the motion of the patch becomes unstable and accelerates. And these three panels correspond to different normal stresses. And we can see that for largest normal stress, such patch becomes small. And in here, they confirmed that this critical patch size is inversely proportional to the normal stress, as predicted from this theory. So far we have calculated the linear stability of the system, but we can also solve how the slip is accelerated by using some approximations. And this is just a force balance equation at the frictional interface. Sigma is the normal stress, and tau is the shear stress, and K is the stiffness that corresponds to the size of the patch. And delta is displacement at the center part of the patch. And this elastic driving force divided by the normal stress balanced to the friction force. And by solving this, we can derive the differential equation for displacement. Okay, so this is just, this can be integrated easily, and this leads to a concrete expressions for the displacement inside the patch as a function of time. And this is with respect to the slip velocity inside the patch, like this. So it states that the slip velocity is the inverse of this function. And because this is a constant, and here delta 0 dot is slip velocity at time equals 0. So this is an initial condition. So as time increases from 0 to some value, then this goes to infinity as this slip velocity look like this. So at time tc, which is expressed by this, the slip velocity is accelerated to infinity. And actually, this kind of 1 over inverse type, 1 over t type acceleration is widely seen in unstable slip of in the experiment. So this describes how much time we have before earthquake. So if we know this quantity beforehand, then we could predict earthquake. But it involves some initial slip velocity on the earthquake fault, and it is virtually impossible to measure such a slip velocity on earthquake fault before earthquake.
Why?
Yeah, because it is very deep, like.
You don't know where the slip is happening.
Yeah. But of course, in experiment, it is possible. So yeah, like this.
They do put these sensors inside the earth, right? But it's not sufficient. Or?
Yeah, usually seismometers and GPS are
On the surface.
deployed on the surface only, and not in the underground.
But you cannot convert this to a surface criteria.
Another important difficulty is that such slow motion before earthquakes does not emit any waves, so that seismometer cannot detect such motion. So detect such slow motion, GPS would be useful, but the GPS is deployed only on the surface. So with a very small displacement in the deep down cannot be detected on the surface. And also another important problem in predicting earthquake from this kind of acceleration process is that even if one could know or one could detect the nucleation process and then see, earthquake is coming, but they cannot know how large should it be. So for example, in Japan, there are numerous earthquakes whose magnitude is smaller than 2 or 3. Perhaps we have almost 2 or 3 earthquakes. So even if we can predict earthquakes, it is useless if we can also predict its magnitude. And to predict the size of the earthquake is a completely different thing than this nucleation process.
It's a random variable.
Yes, most people believe that the earthquake rupture propagation is kind of random process, so one cannot predict it beforehand, how large they are. And this question is related to the comment of Srajit. So this nucleation process can be widely seen in laboratory experiments, but never observed in natural earthquakes. And some people are enthusiastic in detecting this kind of nucleation process. So some Japanese seismologists go to South Africa all the way from Tokyo to Johannesburg. And actually there is a very big gold mine in South Africa. And they dig a hole more than 3,000 meters from the ground surface. And so they dig so many holes. There are many artificial earthquakes produced by the stress change caused by the mining. In that gold mine, we can deploy seismometers and stream meters, which is a distance not far from 100 meters to earthquake faults. But if we set such measurement devices very close to earthquake faults, so far people are not successful in detecting this kind of nucleation motion. This means that even if such nucleation process exists, it should be very, very small. And but theoretical prediction gives that this nucleation size could be as large as 100 meters. But such theoretical prediction based on some simplification, for example, the interface or earthquake fault is completely flat. And also the medium is homogeneous. Of course, for natural earthquakes, the fault plane is not completely flat, as I showed you on Monday. So one must incorporate such roughness in modeling such nucleation process more quantitatively. So yeah, this can be an interesting future work to be investigated. So I think I come to the last slide. So yesterday we emphasized that the rock friction is important in understanding the macroscopic properties of earthquakes. But to do this, we need a friction law. And it can be done only in the laboratory scale. And to understand such laboratory-derived friction law from a theoretical point of view, we could further zoom in to the atomistic scale. So there is a huge scale gap between the atomistic scale to earthquake fault scale, which is tens or even hundreds of kilometers. So to investigate earthquakes, one must inevitably involve many scales. But main focus is, of course, such large scale. And in that scale, the fault has very complex structure. So this rough and heterogeneous structure is very difficult to be dealt with standard elasticity theory. So this is also our important future problem to be investigated. And that's it for my lecture, and thank you for your attention.
Let's thank Professor Hatano for he has finished his set of lectures in the school, and thanks once again for telling us about this
Thank you.
earthquake modeling and some of these earthquake processes. So let's now go for